Hi, so far in the course we have talked about ordinary least squares. Ordinary least squares is an analytical solution to find an optimal set of parameters to estimate a line through a set of points. So it is very suitable for linear regression, and what it basically does is with the linear regression it minimizes the sum of the squared vertical distances from each point to the line. And in many applications this is suitable. So it is suitable in regular linear models, but we also talked how it can work when there's a dummy independent variable. We discussed in terms of heteroscedasticity and time series under what kind of conditions it can or cannot be used. But there are also many applications where assumptions are not met, assumptions of OLS, or where the model is not exactly linear, and where we are therefore not able to use this method to estimate our parameters. So where we can, we prefer it because it's blue, it's the best linear unbiased estimator, but in many circumstances we can't. And OLS is just one among many estimators that are out there. So we have simulated maximum likelihood, regular maximum likelihood, Bayesian inference, general method of moments, and so forth. There are many types of estimators. In the remainder of this course we are going to focus on maximum likelihood. Maximum likelihood you encounter in particular when you do a regression with a limited dependent variable. For example, a variable that is binary or categorical, or where there can be no negative numbers. So for example, if we have a count variable where we count, say, the number of deaths in wars, and we have some explanatory variables why some wars lead to higher numbers than other wars, then that dependent variable can never go negative, and so we cannot just use a linear regression and assume it can be valid on the whole range. Or when the dependent variable is binary, linear models sometimes can work, but it's not ideal, and we'll talk about that much more in the next lecture. So in this lecture I want to talk about the basic principles of maximum likelihood and how to think about these estimators. Now, to get a bit of an intuition what I'm talking about when I'm talking about likelihood functions, and we're going to talk about likelihood functions now throughout the rest of the course. Let's take a simple example. And so it's not an example that is interesting in a social science perspective, but it's an example that is very easy to understand and therefore helps you understand what the likelihood function is. So you might remember we talked about probability mass functions. A probability mass function is a function that for all possible outcomes of an event, of an experiment, show you the probability that that is the particular outcome. So imagine I want to throw a 5-sided dice. The probability that I throw a 1 is 1 in 5. The probability that I throw a 5 is also 1 in 5. So if you wanted to visualize this, you would get a plot of 5 bars that are all equally high, all at 1/5. So that shows you the probability of each particular outcome prior to performing an experiment. Now the likelihood function looks a lot like a probability mass function, or in the continuous case like a probability density function, but it is not quite the same thing. So one thing that you will remember from a probability mass function is that the total always has to sum to 1. So if you have a 5-sided dice, and each side has the same probability of being thrown, then each side will be 1/5 and the sum of all 5 sides will be 1. We know prior to throwing the dice that one of those 5 numbers will pop up, and that means that the total probability is 1. Likelihood functions do not have this feature. So a likelihood looks like a probability mass function, but it's very important not to confuse the two. Let's stick for a moment with this dice example, but let's flip it around. Instead of, in advance of throwing the dice, trying to figure out what the probabilities of each outcome, we are going to ask a different question. We have an experiment, we know the outcome, but the question is, how many sides did this dice have? So let's assume that we have a dice, and this dice can have either 1 side, or 2, or 3, or 4, or 10, or 20, we don't know. We do know that it's greater than 0, and we do know that the numbers of those dice sides are 1, or 1 and 2, or 1 and 2 and 3. Yeah? So we number them properly sequentially. Now, somebody throws the dice and throws a 1. So we don't know what the probability was of throwing a 1 because we don't know how many sides this dice had. This is exactly the question. But we can do some hypothetical examples. Imagine we had a one-sided dice. The probability of throwing a 1 with a one-sided dice is 1. Or imagine we have a two-sided dice. Then the probability of throwing a 1 is 0.5. Maybe we had a five-sided dice. Then the probability of throwing a 1 is 1 in 5. Now we can make a plot that looks a bit like a probability mass function of this equation that I'm sort of discussing, where on the x-axis we have the number of sides of the dice. In this case I'll call it k. And on the vertical axis we have the probability of throwing a 1 if k is indeed the number of sides of this dice. Now this function we call a likelihood function. It shows you the likelihood of the sides of that coin, so whether it's one-sided or two-sided or three-sided, given that we throw a 1. Let's take another example. Again I throw a dice, but this time I throw a 2. So we know that a one-sided dice could not possibly have led to this result. So we know that the dice has at least two sides. If it is a two-sided dice, then the probability of throwing a 2 is 0.5. If it is a three-sided dice, the probability of throwing a 2 is 1 in 3, and so forth. And again we can make the plot. Or let's assume that we throw a 7. We know that the dice cannot have 1, 2, 3, 4, 5 or 6 sides. It has to have 7 or more. If it has 7 sides, the probability of throwing a 7 is 1 in 7. If it is an 8-sided dice, then it's 1 in 8, and so forth. All of these we can plot. And these probabilities are probabilities, but they are probabilities given the number of sides of throwing a particular number. But we've already thrown the number, we know the number that is being thrown, we just don't know how many sides the dice had. Now you could say that if I throw a 2, the highest probability of throwing a 2 is if it's a two-sided dice. Because if it was less, we couldn't throw 2, and if it was more, then the probability of throwing a 2 goes down. So, if we had to make a guess, if we had to make an estimate, how many sides we think this dice had, our best estimate is to say two-sided. Because for a two-sided dice, the outcome that we obtained was the most probable. So the most likely number of sides here is 2. If we throw a 7, then our best estimate for the number of sides of this dice is 7. Because a 7-sided dice has a higher probability of throwing a 7 than an 8-sided or 9-sided or 10-sided dice. But these probabilities clearly do not add up to 1. So if you go back to the first likelihood function, then the probability when it's a one-sided dice was already 1, and then for a two-sided dice was 0.5, so they sum up to 1.5, we're already over 1. So in general, likelihood functions do not add up to 1. It can add up to less, or it can add up to more. So they are really not probability mass functions, which have these defining features of adding up to 1. So let's go back to the kind of statistical model that we've been talking about. So let's first assume that there are no independent variables, just for ease of argument. So then we can say that there is a certain probability distribution around the dependent variable y given some parameter. For example, we might want to estimate, we might assume that y has a normal distribution, and the normal distribution will have a mean and a variance. And so we can say that there are two parameters we need to estimate, the mean and the variance, that best approximate the observed distribution of y. Now, a probability density function would be the distribution of y given the mean and the variance. So given the mean and the variance, we can talk about the probability density function of y. And we can see what values of y are more or less likely. But we can also flip the question. We can say, given that we know y, what is the distribution of this mu and sigma squared? And that is a bit like saying, given that I know what I throw with my dice, how many sides does this dice have? Right? So we can say that y is our throw with the dice, and eta here is k, the sides of the dice, and we want to know, we have this function that is the distribution over the different values of theta that shows you the probability of y. And that's a likelihood function. What is important to realize is that all these maximum likelihood functions are purely parametric. So we need to know what kind of probability distribution y has before we can talk about the likelihood and so forth. So maximum likelihood is a parametric method of estimating parameters. And there are also non-parametric methods where we do not make an assumption about the probability distribution. So a function over the different values of y given eta is a probability density function. But a function over different values of eta given y is a likelihood function. And maximum likelihood is that value of the parameters where the likelihood function is highest. So if you go back to the dice function, if I throw 2, then the value where this function is highest is when it's a two-sided dice. So our maximum likelihood estimate of the number of sides on this dice is 2. That is the definition of a maximum likelihood estimate. So just to be clear, we are talking more or less about the same function, but it's a function that you can either visualize over different values of eta, the parameters, or over different values of y, the observations. If you do it over different possible values of y, we're talking about a probability density function. If you do it over different values of eta, we're talking about a likelihood function. So you can say, given that I know the number of sides on my coin, I can make on a dice, I can make a plot of the probabilities of each possible outcomes. So that is a plot that shows you the probability for each possible outcome given a particular size of the dice. And that is a probability density function. A similar function would be the probability of a particular outcome given different values for the parameter given the size of the dice. And that is a likelihood function. But the calculation of the probability, of course, was the same. The probability of throwing a 3 with a 7-sided dice is 1 in 7. That's the case whether I'm calculating it to produce a likelihood function or to produce a probability function. And so when we think about the likelihood function, we can also formulate it the same way. So we have here a function that is a function of y, the observations, and theta, the parameters. And when we assume that the observations are all independent, the same assumption we make with OLS, if you make an assumption that all the observations are independent observations, they don't influence each other, then the probability for each for the whole data is just the product of the probabilities for each observation. Yeah? So for each observation, for each ith observation, we can look at the probability distribution of y given eta. And you might remember that taking the logarithm of a product leads to the sum of the logs. And computationally, it's much easier to work with sums than with products. So normally we don't look at the likelihood function, we look at the log likelihood function, which is the log of the sum of all these probabilities, or the sum of the log of these probabilities. So let's look at an example. Imagine we have a variable that can always only be positive, and it's a variable where we expect low values to be much more common than high values. Perhaps a bit macabre, but one can think of, say, battle deaths in wars. Yeah? So most battle deaths will be very low, and then in some extreme cases there will be high numbers. So if we want to estimate the distribution of battle deaths across a wide range of wars, we would expect a distribution that is always positive, you can't have negative numbers, and that has many observations, a high probability at the low values, and low probabilities at the high values. So a good distribution for this might be the exponential distribution. So here you see the probability density function of an exponential distribution. A small caveat here is that the exponential distribution is a continuous distribution. When it comes to number of deaths, we are talking about integers, like either 1, 2, 3, but it can't be 1.5 or 2.5. So this might not be ideal, but just as an example. So this distribution has one parameter, the scale parameter, theta, and y is then the observed variable. So for different values of y, we get a different probability of observing this number of deaths, and this is based on, and this probability is then based on this parameter theta. So as we said, when we assume independent observations, so we do not expect different battles to affect each other, so each observation is a separate observation, then the overall probability distribution for all battles will be the product of the probability distribution for each individual battle. So we can use this product sign to discuss the product of all these cases. And then when you take the log of a product, it becomes the sum of the log. Yeah? So we can change this product by looking, instead of at the probability density function, we're looking at the log likelihood function. So we've switched here from a probability density function to a likelihood function because we're going to focus on how it changes for different values of theta instead of how it changes for different values of y. So if you look at this same function for different values of y, it is a probability density function. There are different kinds of outcomes, and these are more or less likely depending on the distribution. But if you look at it for different values of theta, for different parameters, and we assume we have one observation of y already, but we are trying to understand for which parameters that would have been the most likely outcome, then we switched from looking at a probability density function to looking at the likelihood function. And then here we look at the log likelihood function because it's so much easier to work with sums of logs than to work with products. Primarily because when you take a derivative of a sum, it's the same as the derivative of each of the elements of the sum of these derivatives. Yeah? Whereas if you look at the derivative of a complicated product, it gets more involved. And then we can use the rules that we know about derivatives from logs and derivatives from exponential functions to work out what the derivative is of this function. Remember that we're trying to find the value that maximizes the likelihood. So we can think of this as a curve where we try to find the highest point. And you might remember from earlier classes that by taking the derivative and looking at where the derivative is 0, we can find that point that maximizes the function. So that's what we do here. We take the log likelihood function and then we take the first derivative because that is the function we want to equate to 0 to find the parameters that optimize it. So after these derivations, we find that when you take the number of observations and divide it by the sum of the counts of y, you will have the best estimate for this theta parameter that optimizes the likelihood function.